Hey there guys, welcome to the tutorial today. We're going to be going through Pandas and Numpy in Google Colab. The link to where the curriculum is today is going to be in the description, so go ahead and take a look there. Once you access this page, the first thing that you're going to want to do, because you only have view access, is to go to File, click File, and then you're going to want to copy this into your drive so you can use it in the future, right? So you'll save a copy, and you might want to rename it, among other things. So I might change this from copy to live pandas and numpy.ipynb. And this extension ipynb, just in case you're wondering, is interactive Python notebook, right? And so then we need to connect so that we can actually run this notebook. Feel free to follow me on Twitter. I'm always looking for Twitter followers, and then also on Medium. That's where I really post a lot of tutorials and a lot of great content. There's a lot of other great tutorials out there that I've done, like Intro to Google Maps in Python, learning how to build a data pipeline with Bash, and also like Twitter API, anything like that, all on my Medium. And if there's other stuff that you want, feel free to ask for it in the comments. So I have a bunch of different stuff in here. Feel free to ask for other stuff. But for now, we're going to be jumping into what we're actually doing today, and that's going to be learning about Pandas and Numpy. So Pandas, what is Pandas? Pandas is a Python library providing data structures and data analysis tools. The name Pandas comes from panel data. Think about it as a way to visualize and sift through tables of data similar to R or Excel. Don't use Excel. Excel's terrible. I recently had a student who was using Excel, and I was banging my head against the table because he was making changes in the CSV so that he could use it correctly. That's not the way data science works, and that's not how you should be doing it. So always avoid Excel at all costs. You should be able to do everything you need to do between command line and Python. Some benefits: efficient storage and processing of data. Very true. It includes many functions for data transformations, aggregations, and plotting. So pretty much anything you can do in SQL, you can do here. Great way for exploratory work. We call this EDA, exploratory data analysis. And some of the downsides really is it just doesn't scale terribly well to large data sets. So when you have like 1 million plus rows, you'll notice pretty quickly that that is not set up particularly well for pandas. It'll just be slow. That's really what happens. So I threw in here some documentation, which feel free to go jump and look at. But today I'm going to kind of give you just like overview of what you need to know so that you can actually use it, right? So jumping into these code cells, you can run any code cell with a Shift-Enter, and I'm just going to walk through what we're doing here. So the conventions for importing pandas, so you don't have to type pandas every single time, is you want to import pandas as PD. Right? Same thing for NumPy. Import NumPy as NP. Anytime you see NP or PD in someone's code, you can reasonably assume that they're using NumPy and Pandas, right? In addition, we're going to be using matplotlib a little bit today. We're going to do some plotting with that, so we always import matplotlib.pyplot as PLT. This is just another convention. And finally, from numpy.random, we're going to import this rand_n thing so that we can actually make some fake data here in the future. So I'm going to run this with a Shift-Enter. Since this was all imports, we really don't expect anything to print out, right? And I'll just show you real quick what that random data thing looks like just so we can get a feel for it. So we're going to do np.random.rand_n and pass it 3, 4. The 3 and the 4 here are representing the dimensions that we're looking for, right? So we're getting 3 columns, 3 rows, 1, 2, 3 rows, and 4 columns, 1, 2, 3, 4. You may notice that all these numbers are bounded between -1 and 1, which is kind of nice. And there might be cases where you want that. Also, we'll talk about this a little bit more later, but we could multiply this whole thing by 10 and scale it on a factor of 10, right? So there's a lot of cool stuff we're going to be exploring today. First things first, we're going to start exploring pandas. So pandas is actually built on top of NumPy. Really important thing. And that allows it to be really fast. They're built on top of NumPy ND arrays, and we're going to get into that here in a little bit. But our objectives for today is create a series and data frame from Python data types, create data frame from disk data, index and slice pandas objects, aggregate data and data frames, and join multiple data frames. So let's see if we can go ahead and do that. Cool. So Pandas is built on top of NumPy. NumPy is the fundamental package for scientific computing in Python. This right here is the reason I'm doing this tutorial. NumPy is huge. NumPy arrays, or what we would call them, ND arrays, n-dimensional arrays, they're just like lists in Python, however they allow for faster computation. They are stored as one contiguous block of memory rather than being spread out across multiple locations like a list. Each item in the ND array is of the same data type, so they're all integers, all floats, and we'll look into that here in a sec, rather than a conglomerate of any data type that we want. So a list can have any data type. We call this the idea of homogeny. And you know what? That's actually so important. I'm going to go ahead and bold it in my thing here so that I can remember it, right? Homogeny, actually, oops, I made it italics. 2 stars turn something into bold and markdown, if you're wondering. As opposed to the possible heterogeneity of Python lists. Just how much faster are they? Well, let's take the numbers from 1 to 1 million and sum those numbers, timing it with both a list and a NumPy array. So to make a NumPy array, I do NumPy, I name the variable, and I do NP, which stands for NumPy, a range, and I pass it the parameters 0 and 1 million. So it's creating a range from 0 to 1 million. Then I'm going to have my Python list, which is going to do the same thing. I'm just going to use the range function, which I know already starts at 0 and goes to 1 million. Then I'm going to print Python list, and I'm going to time the time it takes to sum the Python list. I'm then going to do the same thing with NumPy. And then I'm finally going to run it with the standard library. So all different interesting things, and ready, set, boom. So we see that the first Python list comes out with 10 loops, the best being 21.6 milliseconds per loop, and our ratio is 0.021. So all of our, that's our average. Our NumPy array, we had 1,000 loops. Best of them took 780 picoseconds, right? So these are microseconds, picoseconds. I'm sorry, I think those are nanoseconds. Let me check that. Nanoseconds. Abbreviation. Let's check real quick. I should know this. Nanosecond. What is musecond? Museconds abbreviation. So let's see what that is. Yeah, so 1 millionth, right? So a microsecond is what we're looking at here. So orders of 10, right? That's huge. And then with the standard library, right, we're still seeing this in the microseconds, even slower than just the Python list. So, and the difference here, right, is we're actually using the standard sum on a NumPy array versus, right, the NumPy sum on a NumPy array. That's the big difference. But you can obviously see that this is much faster, right? And if we were to make these numbers even a factor of 10 bigger, right, those numbers are about to start getting really big. So 215 microseconds, and you'll see that the NumPy array really just completely outperforms them every single time. So talking a little bit more about NumPy ND arrays, we're going to say, so each NumPy ND array has a type, right? And we talked about the homogeneity of these ND arrays. And each array is of one type. So what I do, so I'm going to show you 3 examples. I'm going to show you an example of integers, right, where I make a list of just integers. I'm then going to make a list of characters, and then I'm going to make a list of multiple characters. And I want to see what kind of data types each one of these is. So I'm going to print out the integers data type, the characters data type, and then the strings data type. And so when I run this, we see that we get int64, which makes sense for the integers. We get unsigned int1 for this characters, and we get unsigned int3 for this one, right? And that makes sense. And so when we can look at each one of these in specific, our data type is specified in the array, right, for the characters, for the strings, and then once again for the ints. And if we want to turn this into the ints into a float, we can just multiply them by a float, right? A float is anything that has a decimal place. And so by multiplying it by a float and then looking at the type, it changes the entire data type to float64, which is pretty cool. How are we doing? That's a lot of information. A lot of this stuff doesn't matter too much, but it's good to have as backup for in the future when you're trying to work on this. we're going to jump from here and we're going to jump into creating and using ND arrays. So the first thing I'm going to show you is I'm going to show you my list ND array, and I'm going to turn a list of 5 numbers into a NumPy array, ND array. And then I'm going to do the same thing, but with a tuple. So I'm going to send in a tuple, and I'm going to also specify the data type. I know that it's in 32. And so we can do this, and you'll see pretty quickly that it automatically goes to in 64, but we can change it to in 32, right? So if I put this parameter up here, I think this is going to automatically change this. And so now both these are in 32, right? Useful if you're trying to do stuff along those lines. We also have this shape command. This shape command is huge for multiplying matrices. It allows us to see how big our lists are, right? And our first one, it is 1 row and 5 long. So we have 5 elements in one row. A little bit interesting, but you'll get the hang of it. Same thing with my tuple, right? We have five elements in 1 dimension. So we get 5 back. Now, if we wanted to maybe break into 2D arrays, right, we would have to give it a list of lists. So in this case, I'm going to do an MP array again, but I'm going to then pass it a list of lists, right? So here's a list. So my first bracket's my list, and then inside of it, I have other lists, right? So when I run this, it turns it into a nice little matrix. And once again, you can always use your shape command, right? And if I don't have caps lock on, you'll see that we have a 3 by 5, right? There's 3 rows and there's 5 columns, right? And that makes sense. We can also access specific pieces from here using, so you can access it in using slicing. So you can access individual data, right? Or slices of data. So let's say that maybe I wanted to get the element at 1, 1, right? And we know that Python always starts at 0 for indexing. So we're trying to get maybe the 7 back, right? Because it's over 0, 1, column 1, and it's in row 1, right? Row 0, row 1, row 2, right? So to do that, I'm going to pass it the x value of 1 and the y value of 1, and I get the 7 back, right? If I change this to 2, you'll see that we get 12 because now it's looking for the second row, right? We could have given it the first row, being the 0th row, and then it would have given us 2 back, right? As well, you can say I want the 0th row through the second row, not including, and I want the 0th column through the second column, not including, right? And so then I get a nice little square matrix back, and I can pull a 3rd column here, right? I could also pull a 3rd row. I could always pull it to the end, right? And then I get the whole thing. And once again, just as a little side note, if you put colons in here, right, colon just represents everything. So you could say colon to 2. That's going to give you everything up to the second column, right? Or if I do 1 colon, it's going to give me everything through. So it's going to give me the first one. So starting at this column right here, 2, 7, 12, all the way to the end. I really highly recommend you play around with this a lot. Like I showed you, we can do a shape here, and then we can also just do a sum on all the values in our matrix, right? And if we want more information about what the sum is, we can use this little command right here, and it gives us a nice little doc string on what we can do. And so there's also a find and replace here and some history, but you can do a lot of different stuff. So play with that yourself. We can also sum down the rows. So here, let me actually pull this thing out here so we get it again. Let's see. Maybe I'll do another code cell right here. So here's my thing. So maybe I want to create the sum down each column, right? Or actually, let's I'm kidding. Let's do sums across, right? So my first sum across my row is going to be 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. 6 plus 7, you get the point, right? And so I can sum that, and then I should get a array with 3 left. And so when I pass it the sum with the axis equal to 1, I get that sum out, right? The sum of the first row is 15, the sum of the second row is 40, the sum of the third row is 65. If I want to sum down the columns instead, I just change my parameter axes to 0, right? And then I get 1 plus 6 is 7, plus 11 is 18, and that matches right there. So that's kind of nice, right? There's definitely there's ways to play with it, and you're going to find that this is super useful. Finally, we can get the max, right? And that gives us 15. And I'm pretty sure there's also a minimum function here, right? And we could probably do this again too and get some doc strings, right? So up to you to kind of play with that. Have fun. Broadcasting. So this, I don't know how deep I'm going to go into this. This is one of those things that gets really confusing really quickly, but we'll see how we can do. So first things first, I'm just going to make 3 different NP arrays, right? So I'm going to make one that's just 10 and minus 10. I'm going to make one that's 1 and minus 1, and then I'm going to make one that goes 0.5 for 1. We can run this, right? Take a look at each of these in particular. They all look like we expect them, except one really cool thing is that you can add 2 of these together. So since the dimensions on A and B match, right, we can add them together, and it's going to add 10 plus 1 and minus 10 plus 1, which is going to give us 11 and minus 11, right? Pretty cool. We can also look at C, right, and we can try and add A and C, but since the dimensions don't match, right, you cannot broadcast the shapes together, 2 and 3. So if we were to redefine A and maybe add another value here, and maybe say that's 3, and then try this again, now it works, right, because the shapes matches. So that's one interesting thing. And we can also, here's a nice little case of this, right? So we have A and B, right? We just define those. And then if we add A and B, what this actually does is it does it column by column, right? So it broadcasts. Elements will duplicate, expand, and fill up to make the dimensions compatible for element-wise operations. So when I add this to this, every single one in the top row is going to get 10 added to it. So 10, so 11, 12. Everything in the bottom row is going to get minus 10 added to it. So minus 11 and minus 12. And that's what you can see happens here. Even though these two are not the same shape, right? I can even prove to you that they're not the same shape, right? I can print A.shape and B.shape, right? Even though they're not the same shape, and I guess I should have printed some new lines in there too so you can see. So print, we'll just pass it to \n. So you can see here, right? They're not the same shape, but we still were able to add them together. That's the real thing about broadcasting. It's really cool. Finally, you can also add a scalar value to any value in our, let me do some more print statements in here so we can see what's going on. So first one, right, here's my vector A, 10 and minus 10. I can add 4 to every value in my vector, right? So that would be adding 4. I can multiply each one by 3. You can see that happening. It's pretty cool. This is very useful, right? So you can also, so here's another good example of having 2 different shaped matrices and then adding them together, or trying to add them together. In this case, it's not actually going to work because it can't broadcast to make this happen, right? It can't broadcast 2 and 4 together. So it can't figure out a way to expand this so that you can add a constant all the way through, right? So that's what you got to focus on. Broadcasting is very powerful, and so the note here is it's not clear how it should fill up in this case, so it can't / doesn't, right? Wow, that was a big old NumPy moment. So we're done with NumPy for a little bit. We're going to jump into pandas next. So pandas series are one-dimensional np.nd array vectors with an index. They are built on ND arrays. So we can create a series, pd.series. We're going to put some numbers into it. We're going to print the series, and we're going to print the shape, right? So when I run this, you can see that every value in here, right, has an index as well. Super useful, right? If you want to, we'll show you how to access from there later on. You'll notice it still has the data type. And if you wanted to just get out the as a NumPy array, you just use the dot and vals. I think, can you pass it parentheses? Nope. I think I need another parentheses here. Let's see if I can get this right. Values. So there you go. You can pull it out into just a strictly list, right, by using the dot values method. All right, so next I'm going to create a pandas series of the World Series. Here you go. You can see that we can also put text in here, right, instead of numbers. Useful in a lot of different ways. And so we're going to explore dates next. So dates, pd.date range, pull this up, right? You can see some information on some doc strings on what's going on in here. We have the start string or date like, optional left bound for generating dates, end right bound for generating dates, number of periods to generate, right? All these different things, super valuable. So we're gonna play with this a little bit. So we're going to create a date time index. We're gonna give it the start. We're gonna give it the end. So it looks like we're starting 2015 January and we're ending in 2015 November. And we're gonna do frequency of a month. We're then going to create a series with a random number in each one. So we're using that random number generator. And then we're passing it the index being this date time index, right? That's super useful. So when I run this, now I have a number that's affiliated with each of these dates, right? Incredible. And even just looking at that date time under index series, let's see. Well, I should probably print out this thing first. I'll print that. And then we'll just take a look at this. So you can see that datetime index is pretty much just a NumPy array of datetime objects, right? Pretty useful. There's also some methods that you can do with series. You can do means, right? So you can do dt series.mean, .max, .min. I wonder if you can do mode. Maybe mode? Nope. There's other stuff that you can do here too. Index. So notice how each series has an index. In this case, a relatively meaningfully default index. Pandas can make great use of informative indexes. Indexes work similarly to dictionary keys, allowing fast lookup data associated with the index. Indexes can also be exploited for fast group bys, merges, time series operations, and lots more. When you're ready and in the zone with pandas, you'll be thinking a lot about indexes. So jumping in here real quick, give me 1 sec. I need to just quickly respond to a current student. Let's just real quick. Cool. So moving on, so we're going to do an index series. We're going to do a series. We're going to give it an index for, the index is going to be a state, so California, Alabama, Indiana, Montana, Kentucky. We're going to give it random numbers for each one of those values, and then we're going to also we're going to create a different index series with these indexes, so different states, right? So we'll go ahead and print these out, and you'll see, so random numbers associated with each state, right? And we have two different types, and they look very similar. So Pandas uses the index by default to align series for arithmetic. So if you do index series plus alternative index series, right, we can see that the ones that are in both Indiana, right, and Alabama are in both, so they get numbers back, right? Montana's in both, but the ones that aren't in both don't align, so we don't get a number back. Kind of useful, right? It's pretty impressive that it's able to uses the index by default to align the series for arithmetic. So we're gonna move into data frames. It's kind of big, a lot bigger, but we're gonna start doing this. So Pandas data frames are a set of Pandas series that share the same index. So we're gonna create a Pandas data frame. We're gonna give it 2D matrix, and we're gonna name the columns A, B, C, and give the index foo and bar. When you do this, it looks just like a Excel sheet, except now it's in Python, right? So we could actually do this for larger scale. So we could do a 10 by 5 randomly generated data. We could give it the date time index because we had 10 dates in there. and we're going to name the columns A through E. So you do this, you can see that we're starting to actually get these like tables that we can use, right? So if we want to select just one part of this, we can select just one column using the column name in quotation, right? So if I want just this column, the A column, I use square brackets and then A in the center, right? You can also use the dot notation to do df dot A. Super useful. This will fail if your column has the same name as a data frame method, so you may wish to avoid this notation. Frankly, I would stick with this notation. This notation is useful, but this notation is more robust in my opinion. To select one row, use the dot loc, so you can use the dot loc to give one row back, and you'll see that it's now indexed with those column names, right? That's pretty nice. And so most of the time when your index is 0 through 10, you can pass like a 10 into here and it'll give you back the right one. Column of a data frame is a series, so if we pull out just a column, we get back that it's a pandas series, and so is a row, right? If we pull out just a row, you get back that it's a series. And the columns all have the same index, right? So you can do column.index, and then you can also do row.index, which gives you back the A through E, right? And df through E. So row.index gives you this, df.index gives you this. And then also you can just do df.columns, which is going to give you the same as taking the indexes from the row. So the df.columns, this is incredibly useful because it just gives you back this nice index object. And if you want to break it out of that, you just use the values, right? And boom, it's right there. And you could probably even turn this thing into a list and all of a sudden it's really usable, right? So that's really cool. You can also select multiple columns at once by giving it 2 brackets here, right? That's nice. And then just like NumPy, operations are broadcast to every element of a column. So, right, you could add column A plus column B, and then you could add it as a new column, H, right, and do this. So it's just like setting a key in a dictionary, right? So you can do some operation to 2 different columns and then create a new column by passing it like a new key. And when you do this and then print out our data frame, you'll see that we just added this nice H column, which is pretty useful. In addition, you can use the .loc to select row by label index and column label. So an example of this is, so you can pass it so this would be our rows, these would be our columns, right? This is similar to what we were doing with NumPy earlier. And then you can also set everything in those locations equal to the same value, right? And so looking at this now, you'll see that we actually changed every single value in this area to 2.7, right? Pretty useful. You can select by positional index, so you can do like rows 2 through 4 and columns 2 through 5. Also very useful if you're not trying to use the indexing. And then I'm going to skip over this .ix because it's depreciated, and so because you're not supposed to use it. So let's just delete this area. We're just going to delete that. Oh man, we have a lot of stuff to go through still. Multiple indices. So going through multiple, so start with df with a single index state. And so we're going to run this and we get a nice, so this is from 2015-1 all the way through 2017, right? So it's getting a little bit longer. So let's add a new column of states. So df of state is equal to Alabama, Alaska, Arizona, and we're going to make that longer. It's going to repeat each time. And we can run this, and we add it, and now we have this state column. Reset index, shift the index of a column that gives the row a boring old positional index. So we're going to reset the index so we get rid of these dates, right? You do that, and you see that now all of our indexes, right, are indexed 0, 1 through, and we still have this column index, but we're not using it to index anymore. So we can actually set index as our state and our index, and when you do this, you'll see that now we have 2 indexes with Alabama at each date, Alaska, and so on and so forth, right? And then you can also pull only the locations where you have Alabama back and get only the data where you have Alabama in the row, right? So very useful indexing, and it makes a lot of sense. But you have to be choosing, so when you use the .loc, you have to be choosing by the first index. You can't use this where you try to choose the second index. But you can pass it two indexes, right, as a tuple where you pass it the first index and then the second index. And you can do that and you'll see that this works, right? We're going to go ahead and skip loading data from a file today because I don't actually have it in here. But if you would like to do this, you can see there's some wine data in here, and I'm sure you can find this wine data online, right? But if you want to do this with Google Colab, I would recommend uploading a file here and then playing around with pandas. The big thing I want to show you is the read CSV, right? That's how you read CSVs. You pass it the file name and then maybe the delimiter, right? Usually it's a comma. If it's not a comma, we might have a problem. Let's see if I can just find this file real quick. I might be able to. All right, not in there. So let's see. This is files. Let's see if I can upload. Let's just upload them all. And I can put some links in here. But so now this actually will work for us, right? Oh, just kidding. Because I didn't put it into a data folder. It's just wine quality red, right? So we want to just get rid of that. There we go. So now it's loaded in. We can go ahead and take a look at it, right? Works pretty well. And we can also take a look at the shape, right? So that means we have 1,600 columns and, 1,600 rows and 12 columns. So let's maybe take a look at those columns. Let's see what's in those columns. We have all these different columns and they seem to match, which is a good thing, right? We can also take a look at the info, right? This is super useful because it gives us the number of non-nulls. It tells us the data types. It tells us the memory usage. It tells us the type of each variable. It tells us the number of columns. Tells us the index. All very useful. And then the df.describe gives us counts, mean, standard deviation, min, 20, and then the quartiles and the max. And finally, you can look at the end of the data set using the .tail instead of the .head, and you can pass a number in here and get more or less depending on what you want, right? Next, we're going to jump into filtering. Filtering, we're going to maybe take the chlorides, right, the chlorides column, and maybe we want to see where chlorides is less than 0.08. So we can just do less than or equal. So we can actually just say this. So df/chlorides is less than or equal to 0.08. And we can use this. It's going to give us back a true-false vector. So if I want only the cases where the chlorides are less than 0.08, I can pass this, I can name this thing as an index, and then I'll name it a mask, right? We can take a look at the mask. The mask is just a bunch of true-false. It's just an ND array or a pandas series. And then by passing this mask into the data frame, right, I can just get only the rows where the chlorides is less than 0.08. So we do this, and you'll see right here, all these values are less than 0.08. Pretty impressive, right? So this is cool. What if I want to do slightly more complicated? So you could actually do multiple, right? So greater than 0.04, less than 0.08. You can go pretty darn complicated with these masking things. I would recommend playing around with it a lot. Here's a case where we do the same things, but we only want the columns pH and fixed acidity. And we can take a look at that. We name it df2, and then we get only the cases where chlorides is greater than 0.04 and less than 0.08. And my pH and fixed acidity, and that's pH and fixed acidity are the only two columns I get. I can sort the columns, reset the index, and take a look at the head. And so now I'm sorting based on pH, and it's increasing as we go down. I reset my index, right, because this index is no longer anything meaningful, and that's quite useful. In addition, we could, does this do anything different? I think that's the same. And And so here's a case where I drop the previous index, right? So reset index, drop equals true because I don't need this old index anymore. And there's the first few elements. And of course, you could always look at all of the elements too, right? Next, we're going to jump into group by. So looking at df.head, this is just our first few things. We're going to maybe want to group by quality. So know that this returns us back a group by object. It doesn't actually return anything useful until we perform some aggregations on it. So when you run it, right, nothing actually comes back. But if we group by the max of the quality and then look at the density, right, we can see that we're starting to get quality 3, the max density is 1.008, quality 4, and so on and so forth. Quite useful. We can also group by multiple columns by passing them in a list. It will group by the first column, pass in the first, and then the second column after that, and so on and so forth. So if we want to group by pH and then quantity, and then count the chlorides, we can do that, right? And that's kind of cool. And so you can just see that so now this is aggregating based on pH and quality, and then giving us the value of the chlorides, right? So that's, and the count, the total count, right? And that's what it's doing. So we have one with pH 2.74, with quality 4, and we have one of those, right? And we'll maybe just make this .head so that we don't have to see the whole thing, right? Removing columns, so we can get rid of columns. So this case right here, we're going to try and create the percent of free sulfur. We're going to divide the free sulfur dioxide column by the total sulfur dioxide, and we'll see what happens. And you should be able, and this is going to put a new column in there for us, which is going to be very useful. Running this, we should see that coming in there. And percent, let's see, free sulfur, right? There we go. It's pretty nice. Moving right along, we can drop the percentage free sulfide with x is equal to 1, right? And then, but what happened here is x is equals to 1 is across the row and not across the column. So we still have it in here. But I think if we were to do it the other way with the drop at x is equals 0, I think it would do what we want, hopefully. Nope. I was wrong. So we actually do have to do x is equals 1. And you'll see that it's no longer in there, right? Let's see. So it's no longer in there, right? We dropped it. Quite nice. Managing missing values. There's some more information here on this, but we're just going to, this is just an example of filling the NAs with 0, right? So here's a data frame that has a missing value, the mp.nan right here. And we can just do .fillNA with 0. You can pass it 1, right? So we'll run this. Maybe we want to fill it with 10s. So there you go. It fills everything. And then you can see that it did this. If you want the change to happen in place, you must specify. So you have to do .fillNA 0. So what happened here, right, was it did it and it printed it out, but it didn't actually change it in memory, right? We still have this NAN. So to change it in memory, we have to do the in place equals true. And when you do that, you'll see that it actually does change it. And we could give it a 10 here too, right? And that would work as well. You could drop a row. That's pretty straightforward as well. And there's other stuff in here. I'm going to skip over this right now because we're getting kind of low on time. And I'm going to, so we can join data frames in a similar way we can join SQL, right? Right, left, outer, inner joins the same way. And so here's merge 1 and merge 2. So I made two different data frames. And then if I want to merge them together, I can merge them on inner, right? And I can do merge, I pass the first data frame, and then I do the method .merge. I give it the second data frame, and I give it the inner. And when I do that, you'll see that they actually merge, and that's kind of nice, right? You could do outer here. You can do a lot of different things, right? you can add, so you can concatenate categorical data. There's some more info in here you can play with. And then finally, there's some plots that you can do. So here's a play golf. It's because I uploaded this. So you won't have access to this data, but that's okay. So here's a data frame, right? So I can do a histogram pretty easily by passing temperature and humidity or my column names in a list. I can give it my bins, right? I can do this as 50 bins. It's going to look terrible, but we really only need 5 bins, right? So you can do a box plot as well, right? Pretty easily. You could just take the 2 columns, do dot plot method, pass it the kind equals box. You could also do a scatter plot, right? And so there's a lot of really great plotting stuff in here. And if you wanted to color based on different outlooks, right? Here's an example for that. That's all the time I have for today. So there's a lot more information in here, but thanks for watching today, and please leave a comment if you have more questions. Thanks.